yet.
People are still joining, but we can go. So the way we want to do it is we'll ask Nassim kindly to present his two papers. So on single point forecast for fat-tailed variables and the statistical differences between binary forecasts and real-world payoffs. And then both Marcos and James have prepared some comments on each of these. Fergal, when he joins, is going to present the response from Tetlock in the International Journal of Forecasting, and then I'm going to give a bit of a summary, and let's try to keep it interactive so that we can really grasp the ideas. So I've shown these slides many times. This started off by reading statistical consequences of fat tails. There's about 9 sessions on the website. There's a lot of code, and hopefully in 2023 we can either carry on reading Nassim's new book on fallacies, or maybe the options pricing notes. Nassim, whichever you'll give us access to first.
I see. But I guess it's Marco's turn. Marcos has to start supplying us with text, with text. So it's his turn, and I'll be a commentator. Like he commented on my papers, which incidentally he understood much better than I did. In that case, it won't. That situation won't hold.
So Marcos, you've been put on the
Spotlight, yes.
to the spotlight. You're going to have to do something. So I'm going to stop sharing. Nassim, I don't know how you want to do it. Would you like me to show the papers in PDF? I have them on the screen, and you can just.
I have them in PDF here, and actually the second paper is part of the book, the Inserto, and I think we had discussed it at some point. But I'll just very quickly go through the story of what happened with our paper during COVID, why it is relevant to COVID and other things, especially financial markets, and what it was in reaction to, and it was actually part of the debate. So there are a lot of things involved in the story of our forecast paper, the paper on single forecast and fat-tailed variable, because people are programmed to think in terms of understanding markets means equals forecasting, or in fact, no, for traders, understanding markets means making money, doesn't have anything to do with forecasting, or see. And for scientists, understanding something or a pandemic means understanding its properties. So I very quickly will present the central point. Should I share screen, if you allow me to?
Yeah.
Okay, so I'll share screen with the first paper. Sorry, one second. I have. So sorry, I can't find. I have so many things open, and it hides from me when I want it.
Just let me know if you want me to share. I'm happy to share also.
Yeah, no, just 1 second. It will take, because it's not. Okay, hold on a second. Let me stop and reshare because it was not open. Okay, now it shows. Okay, so this is a story. The Professor John Ioannidis, who is by far the most cited and the most influential epidemiologist, known for usually going against the grain, Professor Ioannidis started producing stuff on forecasting COVID. He and a bunch of other people are criticizing those who made bad forecasts. So our point was that, number one, forecasters and their critics are wrong. Forecasters are wrong to forecast, and their critics are wrong to forecast. Why? There's one mathematical, purely mathematical, coming from probability theory, and another one coming from economics. The one coming from probability theory, as you can see in figure 1, it's not very glorious. Okay, this is a distribution that's not very fat-tailed. Well, skewed quite a bit. It's a log normal distribution at high variance. And the mean is something like 7 point something, as you can see here. The most likely observation is close to 0. So why? Because visibly 85% of the observation fall below the mean. So if you forecast that you're going to be below that number, you're likely to be 85% of the time correct. So that's why okay, it doesn't work. To understand the point again, when the distribution is skewed, most observations are going to be below the mean. So you have a vested interest in forecasting below the mean, and when you're wrong, you're going to be wrong not very often. And so if your penalty is a number of points of how many times you forecast right, correct, or wrong, you're not going to be penalized. Same thing as a trader. There are a lot of traders who say, "Oh, I make money all the time," and usually they're bankrupt. Well, you know, it's like banks. You earn a coupon all the time, and sometimes the company goes bust. The frequency should not be mistaken for expectation. So under fat tail distribution, the thing's actually worse. Look at the mean here for a Pareto distribution, similar to the distribution we found for the pandemics. And the mean is to the right. And of course, most of the time, we don't have pandemics. Okay, the last pandemic we saw was a big pandemic like that of this magnitude, or not, you know, bigger magnitude actually, was the Spanish flu was almost a century before. So that's the probability statement that it's improper. The economists have actually much more interesting view by saying that forecasts can be self-fulfilling or self-canceling. So if you shout, "Oh, this is great stock, it will go up," people buy it. Well, it's going to go up. Someone shouting, "Oh, get out of Bitcoin," and as a person is influential, it will depress Bitcoin prices, and he or she will be correct. So this is why we ban market manipulation. So this is the reason why we should forecast on that stuff. Now there are other stuff that can be discussed here, but this is the main point. Now I stop sharing the screen, and I'm going to open the text of the second paper, which covers a similar point, and it's the Technical Inserto, volume 1. I don't see where I'm screen sharing what.
So we can see page 236, Nassim.
I can't see it.
Oh, you can't see it. That's not good.
Hold on. No, I see it. Yeah, no, I can see it. It disappeared from my screen. Okay, so the selection, no, the distribution, the paper is probability calibration on the fat tails. Yeah, there we go. Okay, here's the paper. That under fat tail, there's something they call probability calibration. Without getting into the details, that is very similar, where people judge you how good you are at forecasting by looking at frequency, not expected payoff. So I went deeper here mathematically, and the other paper is inspired of this one, of course. So by saying there's a difference between binary forecast and what I call vanilla forecast. The regular forecast, you buy something and you buy at that price. It's like an option struck at that price, where you have the full price of the option, the full payoff, compared to a binary payoff. You get 1 if you're correct and 0 if you're incorrect. So and I show why it's spurious to judge people in terms of binary space, in terms of probability, not in terms of expectation. There's a difference visibly between probability and expectation. In full by randomness, I explained the problem as follows. When I was a trader, you know, I was in a meeting and and people asked, "Hey, what do you think of the market?" Publicly, where people were supposed to express their opinion. The problem is it's verbal, so it's going to be in binary space. So I told them, well, I think it's likely to go up. And then that afternoon, the boss came, he was fuming, he showed up. He said, what were you bullshitting me? You said the market is likely to go up, and here you short the market? I said, yeah, I don't see the contradiction. As a matter of fact, it is that's how, as a matter of fact, you should go short if you think the market will go up. He said, what? He said, because the market, when it goes up tiny. And when it goes down big time. So I think in expectation, I get a better payoff being short. So here there's a conflict between someone who's correct in binary space by being long the market and someone who's going to make all the money who's the short. That summarizes the difference between the two. Now there's a lot of mathematics involved where I had to describe things. You see, we option traders, and Marcos will confirm, just like you guys in insurance, we work with term sheets. We don't work with vague descriptions. We like precise term sheets. And immediately you look at the term sheet, what the contract is about, what it stipulates, what it is, and then you price it. You don't go by thing. And so if your contract is binary, which is very, 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 very rare, you have a complete different representation of the world than if your contract is vanilla. In other words, like the regular world, like you buy a stock and it goes up. So here I had to define things, what I say, call away from the verbalistic, by saying, are you realization in, from the of the random variable in say discrete space or finite, or is it's open? So we map the contract, and here I show the difference in figure 11.2, the difference between someone who has an open position in blue. In other words, you have a vanilla contract, you get paid an expectation, so the higher you go, the more money you're going to make. And the second one, who just gets $1 if it crosses that point. And there's a fundamental difference between the two, because under fat tails, and here again, can I, Marcos, can I see you, because so we can discuss? Can I see you? Because I don't see it when I see it, it doesn't show on my screen. Yes. So the best definition of fat tails, what do you think, Marcos, or others are going to be? To me, the best definition of fat tail is the smallest number of observation represent the bulk of the properties. It doesn't tell you tail events are more frequent. It tells you that they contribute more. As a matter of the fattest of all tails is the following, where you get nothing, 999,999 times, you get nothing. And then you get 10 to the 6. Okay. One single observation contributed to all the properties. 1 in a million observation gave you 100% of the properties. That's fat tails. Fat tail is the bottom 4 billion humans having less money than any of the billionaires in America, cumulatively. Okay. That's fat tails. Fat tails is one company in Silicon Valley in the early 2000s, out of 25,000 generating half the revenues. Okay, that's fat tails. So a small number of events determine the properties. And same thing with pandemics. Very small number of diseases have contributed to the bulk of the death from pandemics worldwide historically.
And
So
that's according to that definition, since we in fat tails, meaning that one observation carries much more information than another, than
exactly.
having the payoff, having the, let's say, the vanilla payoff as your as defining your payoff, enables you to get much more information from, let's say, market prices than binaries.
That's exactly. That's exactly.
Because you need a much smaller set of vanillas to infer those properties. Then, because otherwise, if you have binaries, you need how many binaries?
Exactly. You need to have an infinite number of binaries open by every strike, which effectively becomes a vanilla. So
Yeah.
Yeah.
So
if you use a
so
binary
having,
as your atomic building block for an option, you have an infinite number of them. Yes.
yeah.
So so the whole idea is that there's a difference between a regular payoff and the rest. Now I went into psychology papers and noticed that they say, well, humans they tend to overestimate tail events. Well, they may overestimate the probability of tail events. Okay, but the probability is not the point. The point is a payoff of tail events. They still underestimate the net payoff from tail events, which effectively is, you can see it from the option markets. And then, definition of the characteristic scale, here we show that there are classes of distribution that have different characteristic scale. And the fat tail distribution is the limit of, as k goes to an infinity, of the conditional expectation of x conditional x higher than k is going to be constant. Let me give an example. Marcos or someone who wants to partake in the conversation, let's say that if I tell you there's someone taller than 4 meters, in expectation, how tall he's going to be? Because height is still, okay, it's going to be 4 meters. It doesn't exist. It truly existed. Yeah. If I tell you someone is heavier than 400 pounds, what's the expectation? 410 pounds. You see? Okay, so if I tell you someone is older than 0, what's the expectation? 80 in America. But I tell you older than 80, the expectation is 96 or 92, right? Plus 12. Older than 100, 102 plus 2. You see? So if k here is the difference between the conditional, all right, is 2. Okay, older than 120, the expectation is 0. Okay, so exactly. So that's for a Gaussian. So here we have the limit as k goes to infinity of the conditional expectation of x, conditional x higher than k, minus k is going to be equal to 0 for a Gaussian, and it's going to be equal to mu for a regardless of mu, that's for a memoryless distribution. In other words, if I tell you what's the life of the alligator at birth, 20 years. Well, the alligator is not 20. What's his expected life? 40 years. Okay, now he's 40. Here, expected life 60 years. You see. So conditional on, so that's the second class of distribution. And then the third one, which is that the limit is a multiple of k. You see, the limit as k, here I did 1 over k, the multiple of k. So in other words, let's say it this way. If I tell you he has more than $1 million, what's the average? 2. He has more than $100 million. What's the expected? 200 million. He has more than $1 billion, 2 billion. So, and of course it tapers at the end for sample size. But let's say we take companies who sell more than $1 billion, sell 1.5 billion. Companies who sell more than $10 billion is 15 billion. So no matter the number goes up, it doesn't shrink. So that's sort of these other 3 distributions. So the one that has characteristic scale is a Gaussian, which means that as the number gets bigger, the conditional expectation compresses to that number. So the k, as k increases, the conditional expectation converges to k. You see? So there, I use that to explain the following, that that you cannot use, basically the more you go into the distribution type 2, which is sub-exponential, which is where the thing is constant, or the other one you can't use probabilities anymore, you got to use full expectation or some other attributes of probability distribution. I also discussed the spurious overestimation of tail probability in psychology. So they cause us for us, I mean, they accuse humans of overestimating tail probability. In fact, I show that I accuse psychologists of not understanding probability. And there's an error that shows, without going into the details here, because I won't spend a lot of time, I'm going to show the big mistake. There you go. They tend to mistake something that under Gaussian may not be a big difference, but people have the feeling that, hey, you know what? Expectation is probability times expected payoff. No. You see, under fat tails, the difference appears. Here we have here that the sum of probability of, this is the expectation, the sum of probability of every state times the payoff of every state, so expected payoff, is different from summing the payoff, you see, summing the probabilities and then taking a sum of the payoff off of the expected probability. So that's what I call the inseparability of probability, and people make mistake with that. So here I've outlined the central error, because here we have two distinct limits when we talk about probability, inspired by what I explained earlier. And that's here in the theorem 2, that the limit of the one type of payoff to the other goes to 1 and the other one, and the other one is always going to be higher than 1. Okay. And I define them here. I don't want to strain you with these equations because it's going to come later. I'm trying to give an overview of the problem. Okay, allora. So what is the skinny here? And I need 1 minute to summarize. So the central point is that you cannot conflate two probability domains or payoff things. And understanding a process doesn't mean understanding probabilities, but understanding the very general properties. In the first paper, I show in the first paper that effectively pandemics are power laws. We are in the power law class. I'm not going to repeat, of course, because you guys did a nice session on it. It's in the power law class, no matter how parameterized it robustly. If you're in the power law class, you don't talk about probability. What do you talk about? Alpha. You talk about tail exponent. You talk about things. So, for example, who's smart about this? People in Holland. Why? Is there anyone here from Holland? You would notice that people from Holland, well, they don't want to drown. So they don't talk in terms of averages of water levels. They talk about tail properties. And they talk about take exponent and extreme value theory was born there. Extreme value theory is in a chapter that comes before in SCOFT, statistical consequences of fat tail. I don't have the best presentation of extreme value theory. I recommend the book by, if you want to understand it, I just did the cursory presentation of the point, was focused on fat tails, but the Embrecht is absolutely unbeatable as a textbook if you want to understand extreme value theory. But then when you talk to people in that domain, like Embrecht, who say anybody who talks about probability or averages makes no sense. He says, because that's not how you do the business, that business. So basically, it's only psychologists. Engineers don't talk about that. Psychologists, and particularly, those who don't really understand anything else than the Gaussian, and there's primitive in probability. But what Embrechts, they deal with phenomena that have extreme value, and they understand. You don't talk about average. You talk about expectation. You talk about how things couple together in the tail, matters like that, but not probability, raw probability of an event. And finally, one comment that I don't know if you know, but is forbidden to trade the binary options. You see, a lot of binary options are forbidden because they're not. It was discovered over and over time that they don't represent gambling. They don't represent true hedging of anything. As we saw in that graph that Marcos was commenting on, they don't represent an economic value. They're completely different animals. They don't correlate. I'm showing here for fat tails, they won't correlate. For some phenomena, they correlate, but who cares? These are not in the socioeconomic space that we're discussing. Great, thank you very much. And I'll let you guys.
Thank you, Nassim. It's always a pleasure to hear your presentation and your exposition of these things. So James and Marcos, who wants to go first?
James, if you want.
Yeah, for sure. Okay, thanks, Marcus. Thanks, Nassim. To be honest, I had a question. Maybe my questions were a bit more detailed, but I had a question on the binary paper, and that was on the tail var piece. So there's a section on tail var and var. So yeah, I mean the first point I hadn't, because we have var in the insurance industry. Every insurance company in Europe has to calculate the var. That's a 1-year var for any risk across all risks. So typically what they do is they take 30 or so risks they think the main risks are exposed to, and then they work out like the 1-year multivariate probability distribution, and it is var. So they're doing what you had in the paper as not being that good. I think it was confusing. I think it was it K, where the integral from the 99.5th up to infinity.
Exactly.
Yeah. And so were you suggesting that tail var is more appropriate, or
CVAR? CVAR works wonders. Yeah. Exactly, and it's exactly the point. The CVAR is the thing we should deal with, not VAR. Let me explain what CVAR is. I mean, VAR is a case such as P of X higher than K is below what's your level?
Below 99.5, 1 in 200, yeah.
Yeah, below 1%, say, for example. Okay, that is VAR. Okay, so that K is value at risk. No, is that the right definition? So in other words, you have if K is $1 million, is you have no more than 1% chance of losing $1 million.
Yeah, exactly. Yeah.
Yes. Okay. And then the other one is we take K and see the expected loss conditional of X higher than K. You see? So you're taking the expected loss conditional of X higher than K.
Yeah. Okay.
All right. So X being a loss or whatever it is. Okay. So you take these two, and as I showed, okay, on the probability distribution, the limit sum distribution for Gaussian as K goes to infinity, as K goes to infinity, you see, that goes to K. For a power law, it's a multiple of K. And okay, for distribution in between, you know, the exponential distribution, the exponential class, let's start there, it goes to a constant.
Okay, so you're picking up the nature of the distribution in the capital requirements.
Exactly. If the distribution is fat tail, then VAR is not informative. You see, the VAR doesn't inform this one is the distribution is fat tailed.
As I said before, if it's T-tail, it compresses, so it's so close to
exactly. It does compress after a while.
That you can say I can use K because it's close enough to it. But if it's a fat tail distribution, then there is this ratio, and then therefore the problem is then which ratio or which distribution you would use in order to inform that, and therefore then that's the problem of, okay, historical data is not going to necessarily be informative about it. So how do I choose the best distribution and such?
Sorry, I'm trying to answer the textbook online, but I can't type, so I say Enric.
It's modeling extremal events.
Enric et al. Is the author. I'm trying to type it. Someone, I think, Willem Korkman was trying to ask a question.
This one, I think.
Oh yeah, that's the one.
Yeah.
And he again has different basins and different treatments that show. I mean, they don't go into this story, but the properties of the tails are covered by these people.
So
But
James,
what you learn from them is they don't care about averages, and they don't care about probabilities. They care about conditional tails.
James, in for the
The
Swiss
mean
solvency,
loss conditional on a loss is more than 1 million. And this is very useful because I tell people, let me give you a very simple example on how things work. If I tell you what's the probability of today of someone dying of COVID or car accident, odds are dying of car accident is going to be higher, okay, for an individual. But for 1 million, if I tell you what's the probability of 1 million dying of a COVID, or odds are it's going to be from COVID, okay? And if I say, okay, there's a calamity, I'm not going to specify what, but conditional on 1 billion humans dying, it can only come from, although people die of cancer every day and all kind of stuff, but if 1 billion people died on the planet, it can only come from 2 fat-tailed processes: wars and or pandemics. So that's the thinking that you get from extreme value theory.
Yeah. Okay. And so in terms of then, if I mean, it's the regulator who sets that requirement, but in terms of the main argument for moving away from it would be that you're kind of, I suppose, you're penalising some risk types like fat-tailed risks. So you'd have to hold more capital if you're taking fat-tailed risk, for example.
Exactly. Let me repeat your definition, okay? And you're going to see verbally how we can capture the inconsistency, okay? As the regulators. Let me repeat. Let's say the value at risk is that if it's $1 million value at risk, you have 1% chance of losing more than $1 million. You agree? No more than 1% chance of losing $1 million, okay? Now, let's look at this process in which you have a very fat tail. It means nothing's going to happen or you're going to lose $1 billion. Your value at risk is $1 billion. You see, if when you lose, you're going to lose $1 billion, all right? What's your value at risk? Let's look at the process like this. It's a Bernoulli, where you can lose 0 or 1 billion. This is probability 99.5%, and this is 0.5%. What's the value at risk?
Is it a 1% value at risk?
Exactly.
Yeah.
0. There you go.
Yeah.
Okay. So because the 1% tells you how much you're going to lose below 1%. So for fat tail processes, these percentage or these frequency-based stories are absolutely useless. But regulators in finance now, of course, they use CVAR, which is vastly more informative, although they don't know how to calculate it. You need to know future distribution. There's a lot of stuff involved, but at least it's a step ahead, going from VAR to CVAR. From 97, been fighting against VAR to go into something more sophisticated. I think they got it in 2008.
Is that the banking
Sorry?
regulators? Is it banking regulators that have CVAR?
I think the Basel and all these guys, they're going to CVAR now for banks. I think.
The Swiss solvency test, which is the Solvency II equivalent in Switzerland, also is on CVAR. So they adopted CVAR, not VAR, for insurance also.
Yeah, I mean, after we've been barking since I went to Congress in 2008 to present this. And okay, the second point, and they didn't get it before 2008, of course. The second, that's the VAR. So VAR, you know, in this case, your VAR is under 1 million. Okay. The second, so the second thing that regulators do now is they try to do an inverse stress test.
Yeah.
You see, and that is very rigorous because they force you to go non-probabilistically in the tail and work backwards.
Yeah. To
Tell you
say,
what event would bankrupt you. Then
Yeah.
you know here that what event, because it pushes you further into the tail.
yeah, yeah.
In the new book, I proposed something actually to the IMF that we did in the IMF is what I call that's in the second version, it's the second volume of the scoffed, second volume of Technical and Circle. First was scoffed. The second one is, I call it silent risk, where how can you probe risk in the tail? Unless you have nonlinearities like here, you have a threshold effect, you may have acceleration. And this you could see it with Fannie Mae, where the risk start accelerating into the tail, and you can detect it by looking for gamma, if it's short gamma, for convexity. So you do different VARs. You do one at k equal 100, k 101, k 102, see if you have acceleration of losses.
That was the paper for the IMF, right, Nassim?
Yeah, that's a paper. I'm putting them together in a second volume, but you know, I only have one life, and now I'm into bicycling, so it's taken a lot of time away from finishing that volume.
Okay, I'm looking forward very much to that.
Yeah, that would, where you talk about the first one maps, you know, to fat tails, the second one to payoffs, and the matters related to fragility, anti-fragility, convexity, stuff like that, payoffs.
Fantastic. Okay, so there's more reading material for our reading club. I'm very excited.
No, yeah, but I refuse to go in before Marcos is next. Maybe for Gal after that. So you guys can supply.
Good. So at least one paper from Marcos. Okay, James.
Yeah. Incidentally, I updated SCOF. I updated SCOF on archive.
Okay.
It had a lot of mistakes, and I try to thank all the people who found mistakes. So if any of you found a mistake that's not, and their name's not there, and your name's not there, let me know.
Ah, thanks, Nassim.
I will
Okay.
apologize and then fly in to buy you dinner somewhere.
I'll look for a mistake just for the payoff. Okay, let's hand it to James to run through the paper that you'll do, then Marcos, then Fergal.
Yeah, I mean, I only have one more question. I think we've kind of been through some of the paper there, but the main other question I had was on just the sort of areas that yourself and Mr. Tetlock are working in. I wonder if that explains some of the difference in probability, because in the sort of 1950s and older, the people like Fisher and so on were looking at very precise areas like agriculture. And some of the other people were looking at volcanoes, so on. So they were focused on Bayesian areas, and Mr. Fisher was looking at sort of frequentist approaches. But I wondered if there's something in that here, in that if we're looking in finance, you have things like payoffs. But Mr. Tetlock's paper was more in a different domain. It was sort of more where there is. I mean, it was more very subjective things with no data and unknown, you know, less data basically.
I think what we're talking about, the different structure of probability distribution. So what we're talking about is invariant to whether you're using a Bayesian approach or a frequentist approach.
Yeah,
you see,
yeah.
With one marked difference is that if your prior, if you're in a Gaussian world, if you have a prior, and then the whole idea, you start with a prior, you get observation, change your your posterior adapts. So and then you get to a certain result at some speed. Okay, that's pretty much what happens but in a very fat-tailed world. You don't update, you may never update at all, depending on what you're looking for. Like, for example, if you're trying to use observation to get the mean of a Cauchy, you'll never update.
Yeah.
And if you're looking for tail exponent, you'll update. But the difference is when I have the structure of the problem is invariant to whether you're using an adaptive method or just a raw frequentist one.
Okay. Okay.
And actually, even then, the difference fades, because when we talk about fat tail distribution, we're talking about extrapolating observation that you don't see based on a power law. Like a power law, this is what I saw, but then it gives you information about tails you've never seen, and you may never see in your life the tails. Simply, that's the property of a Pareto, as we saw in a few sessions before. Now that eliminates a lot of these arguments between frequentist and Bayesian, because both will converge immediately on the fact that yes, if the structure of the problem is different, then they both will converge.
Yep. Yeah.
And there's also another information I will give, that if your distribution is fat-tailed, and that is central, its parameterization may be thin tails. You will not observe the mean, but the alpha is a thin-tailed. It follows an inverse gamma distribution, which actually, and you converge to it without that many observations. Like you need 1 billion data points to get an idea of the mean, for example, but 30, 40 data points and you have the alpha.
And you can get the alpha, from the alpha you can get the mean, is it?
From the alpha, the mean is no longer relevant, because you never, even if you got the mean in theory,
Yep.
you never really observe it. So it's not a big use on the fat tail distribution.
Okay.
That's another
Okay.
element that you see. Cirillo and I come from fat tailed. So, and then we're talking to Yanir, and then he got it right away. He said, yeah, the mean for us is no longer a consideration since you never observe it in samples. It's an abstract concept that it becomes an abstract concept. As I saw in the first slide, the second slide, you never, the second picture in the slide, when the mean is way out there, you're never going to observe it.
Yeah.
And very often it's an infinite mean, like Cauchy, that has a very nice structure.
Yep.
But the alpha, there's something called the Hill estimator for the alpha, and you can instead of using the Hill, Marco, do you use a Hill estimator for the alpha? You can use something. Sorry.
No, I mean, depends on. At this point, I'm more inclined to start from something like a tree and get a Bayesian update on whether it's going to change from 3 to something.
About the same speed. This is a very minor thing.
Okay. Okay. All right. Thanks for that. Shall I hand over to you, Marcos?
Thanks, James, for coming in. And
So I was preparing because I was preparing to discuss some of Fergal points in case he didn't make it. So Fergal, if you want to go first, then please, so I don't cut you off.
Yeah, sure. I'll say a few things about the Tedlock paper. Is somebody able to screen share on there? And
yeah, I'll screen share, Fergal. Let's go over here.
Thanks, Ron.
So this is, yeah, here we go. Just tell me where you want me to go.
Great. Yeah, let's start with the abstract. Cool. Yeah, I guess I'll start with the title. So, okay, I'm going to mix a bit between sort of pointing out what I don't agree with here and also just trying to maybe back up the paper in what way the authors might try and defend what they're arguing for. False dichotomy alert. So what they're trying to say is that, like, if you want to improve probability estimates, you can still do that at the same time as managing systemic risk. But I guess another way of looking at it is that if you're managing systemic risk, you might not actually need probability estimates. And there's other ways to do it. Look at convexity, look at acceleration or such. And then get into the abstract. If we go back to the paper.
Oh no, I'm so sorry. I was just downloading the new version of Archive, so it switched across. My apologies, Fergal.
It's all right. Yeah, so first thing is like, so the super forecasting approach, what's its purpose or where did it come from?
Is your volume low, Fergal?
Yeah, possibly, or I'll just come closer to the mic, see if that's any better.
Oh, okay.
Any better here?
Yeah, a little better, yes.
Okay. If it's too bad, I can change laptop. I'm on a borrowed one here.
No, it's okay, it's okay.
Cool. So yeah, so I mean the starting purpose, it seems, for super forecasting is for intelligence analysts. So basically US government trying to look at political things. So I mean, to me, that's looking at sort of fat-tailed events, like big magnitude things for the population, potentially to do with military or to do with economics as well. And Tetlock mentions a good few times about false positives. So I'll get to that in the paper. Then there's 2 points, A and B. So in point A, he claims that, let's see, so, yeah, he claims that extreme error avoidance in Nassim's approach. And he also says that there's implicit probability judgments. And in point B, he says that there's an uncertainty on how much super forecasting can improve probability judgments. So basically, how much better you can get at probability estimates. And I'd probably add a point C here, which is there's uncertainty on how much forecasts in general or probability judgments can help with decisions. And to me, there's like a burden of evidence on someone doing probability estimates to show how that's then useful in an application beyond getting the probabilities. So yeah, then dive into the paper. So scroll down a little bit. Again, something Tetlock and Co mentioned a few times is the complementarity. So they're taking the view that their approach can sort of coalesce with EVT and Nassim's approach. And that's mentioned a few times in the paper. And they also accept that the super forecasting approach, it's not really useful for rare events, because you can't sort of create a history of performance for rare events. And we'll see that they look at more like events that are sort of likely to happen with maybe 10 to 90% chance, and then trying to forecast that more precisely. And then mentioning again this tacit probability judgments. So yeah, I'm wondering, what do you think, Nassim? So I guess the way I'm thinking.
Let me start with something quite harsh. I don't think in the beginning, when I tried to collaborate on a paper and visibly it didn't work, in which I wrote 100% of the thing that I stated in that paper, which is a chapter of Scott. My contribution there was transferred to that chapter of Scott, and his contribution was nothing to do with denying what I said or showing that their domains were effectively binaries work. His point was contribution was, because I came up with his domain where the binaries work. He had memory lapses. His contribution was at the level of the finding psychological biases behind misunderstanding probability and conflating one for the other. So you see, that was his thing. So there was absolutely no not collaboration. He claims that happened, but soon after we finished that thing, which was I was translating something from dynamic hedging straight there on difference between binary and vanilla in the option markets and generalizing with the same anecdote as the anecdote about the trader. And then soon after, he got this contract or something to forecast for the government. I said, what the fuck? This, what? No, I pulled out of it and then forgot about him till he started. So he had a conflation between probability and expectation. He could not, they could not, I mean, we're talking about people who could not understand the difference between the first moment and the zeroth moment, okay? And of course, you can't get to higher moments like skewness. And the second, of course, that's the first conflation. That's a severe conflation, okay? And then, of course, there's going to be more conflations later that that appeared. So he couldn't get that one, and then he couldn't get why I call it the masquerade, because he himself used the word attribute substitution, where people present you a result substituting for another one. And that's a psychological effect from which, again, he seems to have fallen. So that's my thing. The second conflation he never gets in his head is that there's a difference between thin-tailed and fat-tailed distribution. Okay, that's one point. And then the other one, they are tail events. He thinks that he conflates fat-tailed distribution with tail events. You see, this is where, and then other things that there's things that are incoherent in what he wrote, like he's asking me to show my track record to prove that that COVID kills, should not use COVID death estimates. Makes no sense. So that's where. So this is why I ignore the paper, but I think now, based on this conversation, I'm going to answer by saying very simply that there's no collaboration, the same points, and no, and visibly, you still don't get that one doesn't replace the other. There are a lot of domains where binaries work, not on the fat tail, so there's no complementarity. You can't say that astrology is complementary to science, that it can help us. Let's not ignore, let's find a synthesis between the two. You don't work, science doesn't work that way.
Yeah,
it all started, the nastiness, I think, to give you some background information, started on Twitter when I was extremely averse to GMOs, which is basically, unlike the vaccines, you're taking the risk for no return, and you're taking a very different risk because you're taking a fat-tailed risk, where vaccines are individual risk. They don't they don't spread it, but there they could have the problem of spreading. And he started getting angry about fat-tailed. He started conflating fat-tailed events, fat-tailed payoff. My business is fat-tailed risk hedging. So there's some stuff that doesn't work there, and I'll rebut in the paper. Maybe I'll publish it on your site as well. So that's my point. I don't understand anything about the paper other than word salad, and you get dizzy when you don't have math to show. I mean, here we have equations that this I1, I2, they don't match one another, and this I have. I don't know.
But is that not maybe a really important point, that for a lot of the, in certain domains, when you're trying to forecast perhaps an event that's happened many times in where your estimate of probability is high, then binaries make sense. But in the domain of severe financial or other consequences with low
or even the military, or especially military.
Mm.
You see,
But
and then we even wrote a paper on wars, Cirillo and I, showing the fattest two tails we found, in other words, alpha that are lower than one, are military and the pandemics, are wars and pandemics. So
but in those domains, it requires a totally different perspective, which is exactly the message of forget about probability and hedge, or get yourself anti-fragile. That's
or
really
understand the structure that you are in that domain. What was Exactly. Our call to arms was COVID in the beginning. We tell them this is a multiplicated process. The only way you can act is reduce the tail.
Yeah.
And how do you reduce the tail? By cutting the contact on the grid.
Yeah.
But by reducing transmission, okay. That was our. They said no, I don't forecast, don't do nothing. Just understand that work with the distribution. A probability distribution has more than one moment. Okay. Some people stop at zeroth moment. Some people like Ioannidis went to the first moment. That's not how it works. It has infinite moments. Okay. So you look at the shape of probability distribution and look at what experts have done who have dealt with tails. Okay. Namely, there are some parameters of some heuristics we can to discuss the tails, but they're not the probability ones. And again, the best one is discussing things such as the scale, the alpha. This is what we think we're facing. Let's lower this. Let's lower the alpha. You see, let's clip the tail. How do you clip the tail? Close or test at airports. That clips the tail.
Yeah. And the trend.
And also don't judge people. Think about it. The worst to say, oh, this guy is super forecasting will find a good forecast. You can't because it's recursive.
Yeah.
You see, if the government say, oh, 1 million people will die, everybody will get scared, nobody will die. Is it a bad forecast? No. But it's a definitely not a wise approach on their part to produce a forecast, and it's even worse to criticize it. So both sides were wrong in that forecasting business. But let's talk again, in macroeconomic world, you see the alphas are usually between 2 and 3.
Yeah.
In economics, in macroeconomics world, between 2 and 3. Pandemics are below 1. And in the physical world, you get alpha between 1 and 2, say earthquakes about 2, and other phenomena, about size of cities between 1 and 2. So understand the alpha, what alpha you're facing. That's a lot more information than any kind of bullshit about probability.
Yeah. Got it.
You see, that's what. I mean, this thing is Tetlock's answer is not the important things. For us, the important stuff is for us and our business to understand the difference between basins. There is a difference between these two classes of distribution, which we've been talking about now for 9 sessions. Okay, and the consequences as to what information you need to act upon. You see, which is completely different. Actually, the first paper has a very interesting dilemma that we show, that we discovered, is that forecasting the rate of growth, okay, forecasting the rate of growth is thin-tailed. The rate of growth of the pandemic can be thin-tailed, but the number of people killed would be fat-tailed. And we showed it here, I think, in there's somewhere, did we show it? I know somewhere I've shown it. It's definitely, yeah, there we go. I'll show it on page, whatever, on page 4, where we show that if you have the rate of growth, okay, because the error of rate of growth changes a little for the growth, but given that it's exponential, the thing blows
As
up.
as soon as you exponentiate, you either get a log normal or a power in the number.
Exactly.
You've got minor perturbations in the rate of growth. So all of your CRR type models where you're trying to model the rate of growth is just never going to work.
Exactly.
And CRR.
And let me give you a little trick that I didn't put in SCOFT. Ron, great. So if the rate of growth is Gaussian, it would be log normal. No?
Log normal.
Okay. But if the rate of growth is slightly thicker tail than Gaussian, if the rate of growth is exponential, the other one will be power law.
Yeah. Yeah.
You see?
Yeah.
With infinite mean, with a finite rate of growth, you get an infinite mean, so long as the rate of growth is volatile.
Yeah. Yeah, that was one of the fundamental issues I think I understood from this paper, is that if if you exponentiating something with an error term, you're just going to land up in a mess. And that's all the SIR models. And it's just interesting to think about other model classes where you've got the same issue potentially. That you basically got to put a prior or an error distribution on your rate of growth and simulate from that, and then you'll see something like exactly like we've got in figure 3 here. Until you do that, you've got nothing. Okay, good. Okay, Fergal, back to you.
Yeah, sure. Yeah, I guess also for sort of the way I'm looking at this when I've read the paper, I think so. If we are we on the same one? Yeah, cool. Yeah, so in this paper, I think basically what they're doing is looking like all these super forecasting bets are like, what's the probability of an event exceeding or being below a threshold? So it's looking basically at the sort of the CDF and the survival side, so probability of surviving greater than different thresholds and making forecasts on that. And to me, there's sort of information loss. So like if you look at it like an S-curve, sort of with your CDF, with your cumulative distribution S-curve, there's like information loss where even if you get good on the probability side, you sort of lose all the magnitude information, especially as you get into tail. So that's sort of how I think about it. Easier probably with a diagram, but
it's also interesting if you think about how you move from your probability to your magnitude with a lot of distributions. If you think of your inverse probability transform, you're often exponentiating that probability somewhere along the line. And that becomes quite interesting also, just based on what we were saying before, that a small error exponentiated has a massive outcome. I think that's exactly the issue on the CDF. You can get quite accurate. Maybe you can get quite accurate, but a small error translates into a massive.
Yeah, exactly. There we go. That's bingo. Ron, you answered. You see, I tell you, I learned more from you guys than I have in my book. Exactly. This is the CDF. An error doesn't change much to the CDF. It changes monstrously the payoff function. But plus, there's another interesting thing that we learned as traders. If you do a mean preserving, a variance preserving transformation to fatten the tail of a distribution, so you take the same distribution and you fatten the tail, okay? The binary option goes down in value. The vanilla option goes up in value. You see? Take a strike K for an out of the money option and just change the distribution.
Yeah, this is similar to the paper on forecasting election probabilities as a martingale. I think that's where we made the point in Scoffed.
Okay, yeah.
Yeah, very good. Okay.
That's something in dynamic hedging. That's the last part of dynamic hedging, which is a very old book that was focused on, because we all got caught. We say, oh, tails are fatter, let's buy binaries, and then we realize that boom, you get shellacked, because what does fat tail mean, to repeat? It means the smallest number of events determine the bulk of properties. It also means that it's not going to exit the tunnel, but when it goes, it goes. You see? So if you're fattening the tail, you're lowering the probabilities, but increasing the expectations. I'm lowering the probability of hitting K, but should it hit K, it's going to be a lot more. Something like this, of this type.
Got it.
So they go in opposite direction. The binary and the vanilla go in opposite direction.
Yeah. Good. That makes sense.
Yeah, and then I guess this paper is looking really at the binary.
All about the binary in this one.
So then he talks about like focusing on things between 10 and 90% range. So basically trying to look at the body of distributions without looking at the tails in a way. Then there's mention, but not the detail in the paper, about extracting wisdom from crowds, which sounds interesting as a concept, essentially the same thing that markets do in general. And then, yeah, so he says then if we skip on to sort of the top right of the same page or the previous one, he says then, like, is there zero value in forecasts for policymakers? And yeah, I'm curious, what do we think there? Like,
Yeah, I think Ron just answered them.
yeah,
You see, Ron just answered him. He's shown now he's shown you a CDF, okay, comparative CDF, okay.
okay.
That a small error in this, okay, translates into huge error and payoff. This is useless.
So
I mean, I
then,
don't have to explain it to them; they won't get it. But Ron just explained it 5 minutes ago.
Yeah. So under fat tails, the forecasts are useless, or is there some element of ballparking that's useful?
I don't think in probability space. I mean, if you're using the wrong approach to start with, you see, if you went to Holland and start talking probabilities and counting and so forecasting how high the sea level is going to be and taking forecasts, they laugh at you. They may even deport you. Okay.
Yeah.
So it's a wrong approach. A bunch of psychologists are used. Why are they doing this? Because they're used to doing the difference between perceived probability and actual probability.
Yeah.
You see, but I'm saying a small error in probability is robust, but it has small errors. A small error in probability compounds to a huge error in payoff.
Okay.
So this is why you can't really look at the CDF. Ron just explained it 5 minutes ago.
Okay.
See, I learned more from Ron than I put in my paper.
I guess the other interesting thing is where I have a doubt, and I mean, I've never worked in the military, but saying that a small scale naval clash is 6% or 8%, I really struggle if a decision maker is going to make a huge change in what they'll do on that basis. I guess it's a different point that is there actually value from a military style decision maker in knowing or having what's purportedly a slightly better estimate? If you have to do something about the probability of there being an event being, say, 15%, you probably have to do the same thing at 12.5%. It's very difficult to understand that you have as quantitative a decision maker as seems to be indicated here. In my experience, when you try to bring in even a range of estimates to decision makers in the corporate world, there's very little difference, and there's not that much interest in the exact number. If it's a big range, then you do one thing, and if it's a small range, you do another. But how much value could there be, even if you believe that the super forecasting program can give you a slightly more refined estimate? Is that actually meaningful? I really struggle to understand a situation where it would be particularly meaningful outside of a betting, gambling.
And especially because even at the beginning of the super forecasting book, there's lots of ambiguity when you present someone with a probability estimate.
Yeah.
It's 10% less improbable, still not probable. It's going back to the elections, it's 70% chance, meaning, okay, it's a victory. Is it confirmed or not? So
yeah.
So using those kind of
Exactly.
probability estimates
Unless you've got a very
even then, it's you're. What does it mean? Okay, is it a probability in the ensemble mode? Is it a probability in terms of? So you're not going to have an ensemble. You're not going to have 10 parallel words, and you can choose and pick, or you have the average result or something.
I mean, I'm not a military person, but unless you've got a really super well calibrated sort of model that survives on these extremely well calibrated numbers, is a 7.5% really so different from a 6.5%? It seems very difficult that is actually going to produce something of huge value. I don't know.
Even okay, let's look at even then. Let's look at a less let's say serious thing. I mean, one of my pet peeves is looking at NFL analytics and say, okay, if you choose to kick the extra point or to go try by two, oh no, there is a 46% difference or a 47% difference. It doesn't matter really. I mean, which are your players? Which is your condition? Are your players playing better than the other players? Is your team the underdog, and so you benefit from trying now instead of going to overtime? So there is on the slides I try to get into this, which is there is this temptation of using the analytics and prediction to justify some decision that you want to make, and that is probably one of the things that I want to discuss later, which is that, well, the program exists because someone is paying for you to produce numbers. Well,
exactly. Someone's paying you to produce numbers, and someone is using them for therapy, basically.
Or even worse. I mean, even worse. I mean, because if they could be using to justify some policy decision that is not necessarily, you're just using, okay, do this analysis and get me these numbers because I want to use those numbers to justify the decision that I already have in terms of what I want to do. So military people, if they have, let's say that you have really, you are in a live war situation. The problem is that you have constraints, which is okay, material, people, and territory, and the time. I mean, and the time. So you'd say, okay, what is going to give me an advantage? In most cases, this is what I'm going to do. So this is probably something that, and they will try always to get, let's say, the question of, is this choice going to lead me to a big chance of a small victory, but larger chance of a decisive defeat? We cannot forget that most of our lives are sequential decisions. They're not ensemble decisions. So the risk of ruin is going to clip every possible path or something. That's why just looking at probabilities is not really informative of why people make decisions in real life. People are not, they do not survive because they made better probability judgments, because you might even know that what you're doing is not is not in accord with the most probable path, but you're doing this because the probability of ruin is high enough that you cannot take that path. So,
yeah, there's one thing I want to strip in one point that more relevant. That's sort of to real life than this. More to the points I made earlier, to real life. In real life, you never pay the probability. You see, like I remember a fellow in the pit telling me, we don't eat probabilities. It's not a raw material. You don't eat it, all right? It's not, doesn't really. So it's fine for bureaucrats who want to for papers, but you don't eat probability. So you don't have a mechanism of skin in the game of selection. You see, you're not paid, there's no money exchange. There's not, except in gambling, and gambling is Gaussian, and there, of course, the casino eats your probabilities. So, but in finance, we don't have that. So this is why these guys will never be selected to be fit for the real world.
What if we take the tin-tailed case? Is probability fine then? Maps okay?
Yes, but a thin-tailed probability, like in the casino, for example.
Yeah.
Okay, so you're paid in probability, but there are not many cases where you are paid in probability. In the socioeconomic world or in military. In medicine, you are, but they would laugh at you if you came in and start having super forecasting. You see, in medicine, they just take the estimated procedure because they don't want the forecast to rely on forecasts, they don't rely on empirical data. You see, they give you the procedure, they tell you, well, there's 3% chance of death if you do this, whatever. If you want to say you want to change, well, you want to change brain, okay? Want to borrow, do Elon Musk and alter your brain. Okay, tell you 3% chance of death, right? Something like that. And then they give you a range, all right?
Yeah.
And that's unconditional. But with this doctor, we know he's incompetent, it's 10%. That they won't tell you, but they will hint. So that's in medicine. This is why it probably works in medicine, but but you don't need a Tetlock to come in with his army of forecasters to try to tell you, well, these guys are good at forecasting this procedure.
Yeah, there's a fundamental difference in the type of probability domain. So if it's something where you've got multiple trials or large N, then we've got many good ways of quantifying probability. You fit a machine learning model and it will tell you very precisely what your parameters are. But in this sort of subjective domain where it's N equals 1 each time, it's very difficult there to believe that a slightly more accurate probability estimate, even if it is possible to get that, will make a huge difference in the decision maker's outcome. And I've never observed a domain like that. Maybe there is such a thing, but I've never seen it. I think distinguishing between the type of domain of probability is very important. And that's, I guess, one of the main points here, that this seems to be a somewhat contrived domain compared to the other places we're familiar with.
Exactly. I mean, it's sort of like IQ. IQ is, they say, well, we're going to measure IQ. Why? To see if you're good at your job. And you say, if you're good at your job, you don't need to measure IQ. So it's just like, effectively, even if it worked, you don't need it. If you take the track record as a job, track record as a doctor, as a dentist, whatever, that's where you go by, not the IQ. It's the same thing with this probability. So a super forecaster, you don't need it in domains that are Gaussian because you have a lot of data and you got the data. So what would you do super forecaster
exactly
for?
If there's a lot of data, fit a deep neural network or boosted trees and forget about it. Go home. The computer does it much better than you ever will. And if it's not, then it's really hard to understand what you need this for.
Yeah, we can talk at the end when we do the recording if we want to write a joint paper, or should I write myself a rebuttal, because this is addressing me. Or if you wanted to join, because the ideas anyway, I've taken them from you. So if we could draft, and then we'll get all our names. We're guaranteed to have a publication. You see, someone attacks you in print in an academic journal, you're guaranteed an academic publication.
Yeah. Okay. At the end, we discuss.
What? We'll discuss. We'll record the recording. I will discuss.
Yes. Okay. Back to you, Fergal. Where else would you like to go?
Yeah, let's hop on to the plot on the next page. Yeah, look, same thing we've been discussing really. So there's a mapping of like performance using false positives and true positives, false negatives, whatever way you want to look at it. So this actually works for thin-tailed things. So I work in like energy, electricity, and we use this for similar stuff for wind forecasts, which also they're bounded between like min and max. But yeah, if you've got unbounded variables with fat tails, you're not counting magnitude when you look at a true positive or a false positive. It's all binary here, like right or wrong, true or false. So really just the same thing we've been saying about this is looking probability domain and missing magnitude is how I look at it. And then unless any comments, we can scroll down to the division of labor comment.
Would you mind helping me find that? Let's just see division.
Sure. It's basically the bottom part.
Page 3, yes, page 3 below the
Here we
chart,
go.
I think.
Yeah, there we go.
Yeah, there we go. Yeah, so like the approach this paper is going for is like, okay, you've got two kinds of people. You've got people who predict probabilities and people who apply a function on top of probabilities based on their values, and sort of trying to say that the probability people can be value neutral, and then the actual people making decisions can apply values on top. But yeah, I think it comes back again to a lot of this, just we've already said. It's like the mapping from probabilities to exposures, or what actually matters. It breaks down if you're dealing with these binary forecasts, which don't capture the magnitude. Although it's an interesting one to me because so I'm an analyst in energy, and there is a bit of division of labor. I do like the analysis, more coding, and then the traders do the actual putting positions on. So I'm always trying not to be too forecasty and to be looking more at like understanding the system, adding insight in that way. But yeah, dividing labor into like probabilities that map to payoffs, then I think you lose the magnitude. You really need to, even looking at fundamentals, you need to know what the purpose is that you're trying to solve for. Then what else do we have? Then there's talk on the right about a winnowing mechanism. So at the end of that paragraph, yeah, here. So the paper is saying like, oh, but you know, it's costly to do things and you might have limited resources or have to prioritize between things. And how do you do that? And can we use probabilities? Maybe you need probabilities to do that. But of course you can do it with methods that consider magnitude. So looking at convexity, acceleration. I think a good example here is the COVID paper that Nassim put out in like January when COVID was starting. There was no probabilities, but it still was able to look at like, this is a significant thing that's coming up. So it was able to like identify this matters, apply the principles of basically exposure, and not using probabilities to do that. So we do have a winnowing mechanism to decide what to focus on. Then we can hop to the closing remarks, next page. So let's see what's interesting here. Yeah, so a lot of this we've said already. I think one thing is like people like having a clear picture, and people feel comforted by numbers. Like, here's a probability. So I've just been thinking about if somebody asks like, okay, is this like new disease a concern? What's a clear way to communicate that? And at the moment I'm on like, you try and explain it wholesomely with like, just look at the broader picture. But yeah, I'm still thinking about that, how to like communicate to people that what your method is. And so it doesn't sound too foreign, because like sometimes if I start explaining the convexity things to people, they're like, I've never come across this before. I don't know what you're saying. And if you describe it in a probability sense, people are like, they feel like they've understood, even if it doesn't make sense to give probabilities. Not sure if that was clear. I don't know.
Yeah, no, you're right. It's just that the therapy.
Yeah.
Yeah, you're vague. Give them a probability. You communicate with someone. If you're vague, the person may have anxiety. If you have a given probability, they feel better. Well, that works in medicine. If you want to have a procedure, they tell you, well, you have 99.9% of succeeding, chance of success, you feel more comfortable about it. In this case, they're just bullshitting you on N of 1 events, N1 events.
And then with fat-tailed domains, is it just that you can't compress a lot of these things into like a very simple answer? Like you need to have.
No, you can, but not using probabilities. That's the point is you can show the alpha distribution, how fat-tailed it is.
Yeah.
You can say these processes are fat-tailed, just mitigate them quickly.
So then, is it like transferable to all problems that you can take an alpha approach? So then people are familiar with what you're going to do. You're like,
yeah, the alpha is not the only dimension of a fat-tailed distribution. It's a dominant one. You also have to give the scale, but at least you can explain that you have a situation of this type of uncertainty. And with the alpha, you can definitely say that conditional on losing X $1 million, odds are, okay, it's going to come in one block, and it's going to come from this, not that.
Yeah.
Like I say, it's a pandemic. Heart attacks kill a lot more than pandemics today, but conditional on 20 million Americans dying in 1 year, it's 100% going to be like 99.999% came from pandemic.
And if you're say your government with limited resources, if you're prioritizing, are you trying to focus more on the things with basically fatter tails?
You focus in the fat tail domain. The way you do it is you focus on payoff. You don't focus on probability.
Okay.
But if you follow the rigorous approach of extreme value theory, it will drive you there.
Okay.
You can mathematically show that you should focus on payoff, not probability. That's what I tried to do in SCOFT.
Yeah.
You see, the whole thing is we can mathematically show that it's not mathematical to use probability but focus on payoff. Yeah. Because of a class of errors, because of a bunch of things. But I think that the problem is not even there. The problem is way below, is still not understanding the difference between domains.
Yeah.
Yeah.
The consequence of that difference between domain doesn't even hit him. It doesn't register.
Good. Fergal, anything further here?
No, all good.
Good stuff. Okay. Let's hand over to Marcos for his slides, and then I'll summarize quickly at the end if there's time.
Okay, let me try to share my screen. Just a second. Can everyone see the screen?
Not yet, Marcos.
Okay, let me try again. Okay, hold on a second.
You need me to share for you, Marcus?
Oh yes, it probably has. At some point, probably a system update made the Zoom lose the privileges of sharing the screen. So if you could do it, it will be faster.
Here we go.
Okay, so there might be some typos in there, but let's go through it. So we're going to discuss a bit about the problems of broken response, and also a bit about the payoff versus probability thing. So the question is that you see that on the website means that they are trying to say, you have not only you have a precise probability forecast. So that means that that is probably trying to give you that comfort and say, well, not only you have a probability forecast, but it's good and you can trust it. Is as nothing said, it's therapy. But the problem is that why is being used as it's not being only used as therapy. You want to use it in a kind of bad way. Can you please go one slide further? James, sorry. So let's look at how a real prediction works from. So there is a nice paper by Ian Clark and Seidaman that's implied distributions from risk reversals and implications from backed scenario, in which they look at the implied volatility from FX options, which are very liquid. And they look both at dollar GBP and euro GBP. And they are looking ahead, not forward. So that allows you to get fat tails that were never observed before. And if you sell that option, you have real monetary consequences. It's not just, oh, I'm wrong, pity. Well, when you're wrong, you're really wrong. So we can see on the next slides. So they plot the implied distributions as time goes by. And so the red one is just after the event, but you can see that the implied distributions, you start having almost a bimodal distribution on the outcomes, and because the election, the referendum was really close, and so therefore you always say, okay, if it goes this way, you go one way. If you go this way, you go the other way. But that implied distribution from the option prices tells you by how much, because if you sell a vanilla, it makes a difference whether it ends at 137 or 135. So the interesting thing here is that if you can zoom in just on the area below, yes, exactly above 135 to 140, you see that the tail on the Brexit wins side, it goes really, really further down below. I mean, meaning that people are not selling the 130 option cheap. Compare this with how, let's say, on how this would be different. So that means that you really, it's the only real way to get predictions that matter. It doesn't matter. I'm not trying to predict whether it's 135 or 134. I want to know that, okay, if that event happens, then what can happen and how it happens.
Yeah.
So this is the kind of prediction that I can get information that is useful with and has economic consequences. Because if I want to hedge myself, yes?
Marcus, is this the p-value or the q-value? The q measure or the p measure?
So this is
This
this is the risk neutral.
This is
this
Q
is the
measure.
risk neutral. Yeah.
So but let me tell you one thing: the difference between the two, nobody would ever know. Nor does it really matter.
Yeah.
You
But
see,
then
because
the question, so
Go
I
ahead.
was just saying that if you want to hedge yourself against
that's what you
Brexit,
get. It's a
Yeah,
sort of
this is
nifty problem.
what matters.
Exactly. So the market is not telling you this is my forecast. This is equivalent to saying, is a forward British pound price an expectation, or is it an arbitrage relationship between today and the future? It is an arbitrage relationship. Same thing here, except that at some point there is some kind of preference built in the market that reflects indirectly.
It's beautiful.
So yes, so this is the kind of thing that, okay, the information that I extract from option prices is a probability distribution. But I can see that in this way I can get much more detail on the tail of the distribution than if I were to just try to interrogate people about how would they price a binary every 1 cent. This is a much better way of doing it, because if people are really fearful about that is the same thing as going back to dynamic hedging, was when you say, well, I want to buy this out of the money option. One trader said, oh, you can have them as many as you want because this is not going to happen. The other trader said, wow, my price is this one, because I'm not selling that because there is a consequence on that. If I remember correctly from what you wrote before, Nancy. Is if the first trader that will sell you the really deep of the money option at any price because this is not going to happen, he's doing the error of just looking at the probability distribution. He's not really thinking about, as he should, about the consequences. So the next slide is
with this one. So we have probability distribution, but we've been saying like you don't want to look at probabilities, you want to look at payoffs. So how do you extract value from looking at the implied probabilities?
No, but it's the problem. No, it's
They show on the line.
because when you talk about because the probabilities in the when Tetlock speaks about probabilities, he speaks about a point estimate of probability. He's saying this kind of event.
Exactly. You have the whole distribution. You see, you have the whole distribution. Yes. So you can see the payoff. You can spot it from looking at that.
Yeah.
And this is inherently a payoff probability. So it's your empirical adjusted for the cost of hedging.
If you multiply this by your payoff, then you have a value for the option.
This is Tetlock is trying to get the P measure, Fergal. This is the Q measure density.
No. Tetlock is looking at kind of easy to answer
yes or no
questions.
It's binary.
Yes or no or something. Or no. And he's trying to say, okay, so if you go to the next slide, it becomes easier.
Okay.
So what is the typical reward function, the Breyer score, in which I'm looking at, oh, okay, I have lots of events and I have lots of predictions, and I'm trying to see how close to the average outcome I was. So in other measuring how well I predicted the probability.
Ron, one comment on a difference between P and Q. For us in probability, let's put it this way. The difference between P and Q measure is not significant because it tells you that the implied probability distribution does not have risk preferences built into it. That's the important thing about it. Rather than, and if you put it in the Finetti's world, which who actually popularized or maybe even formalized the bias score, the Finetti, for him it probably doesn't exist. It's an opinion unless you bet, and it's your choice price, the price at which you buy or sell.
Yeah.
That's the probability. Okay, and therefore in his world and in that world, the probability is an abstract thing. You see, so it's just like words, unless there is some kind of concrete things mapping to it.
Yeah.
And also the no arbitrage. So for him, a probability is something that avoids a Dutch book argument, which means you
Common
end up
Dutch
trading
book
against
argument,
yourself
yeah.
and joint things. So we have a map of the world that is consistent for betting. That's the Finetti. And for us, a version of it for us is that P, you see, that Q measure. In fact, and the difference between P and Q is really academic in the sense that it's like saying, is a dollar against euro an expectation or is it supply on demand, right?
Okay.
And
Yeah.
someone would say, what the fuck is the difference?
Yeah. But I suppose
Yeah.
what you get with the Q measure is, well, that's actually something with a consequence attached that you could actually trade. So it's much closer.
Exactly. You can do something. If you don't like it, you buy it, and then they should converge. That's it.
Yeah.
It is risk
You
neutral.
can-
That's the beauty of it. That there's no risk preferences built into it. That's what the central element.
Yeah.
Is that what the market is producing to you, stripped of all risk considerations,
Yeah. Yeah.
based on the
So-
other line. The other line may have some risk preferences, but that's another business.
Yeah.
So one of the problems of that reward function is, okay, if you have, let's say that you are trying to predict a rare event. So if you just say no every time, and you get you're wrong one time. Oh, okay, you're wrong one time, and you are right 99% of the time. Okay, so you're really good. So that's one problem.
What happens if you did an adjusted Bria score using the Pareto likelihood, Marcos?
I haven't been into that yet, so
should-
there are other measures. I think that the paper, nothing lists 7 different reward functions. So the M4 and M5 competitions have used a much better calibrated function to judge your predictions. But the other point is that when you are in real life, you're not predicting the fact that you get wrong. You got wrong first and then right makes a difference. The best thing to think about is the Joseph story. About the most notable thing was that Joseph predicted, okay, 7 years of aperture and 7 years of famine. And let's say that he got the first year wrong, but then the other 13 were right. And retroactively, one could say, "Wow, he was a really good predictor. He was a super forecaster." Well, he would be if he was wrong in the first year. People would throw him to denial and forget about it. So. There is a point that we in real life are making lots of consequential decisions all the time, and you don't get the chance to be wrong in some of them. Let's say that you are let's say you like to go to restaurants. You like the variety of restaurants, but the thing that proportionates to the variety of restaurants is that most of the restaurants will fail. So there is so you need someone who is willing to take the risk that he is going to succeed in order for you to enjoy that. So So there is a markedly different reward function that, oh, okay, I need to be successful in the first quickly. Otherwise, I am out of the business. So the chances of you having a bad meal are, well, if you had a bad meal in a restaurant once, you don't go back to the restaurant. But so you are always on average having a good meal, but the consequences of that is that on average restaurants fail. So next slide. So it's something that Fergal described also, the domain restriction of super forecasting. So you look for something that you have either repeated occurrences or repeated non-occurrences in that you can judge it quickly. So, and you have it, so you have either this frequent time series, so let's say monthly economic data or some discrete event. What is the problem with that? We can see that on the next slide. The important questions by definition are unbalanced, because the important thing is that will the surprise on that thing be enough to matter? Well, if it's important enough to matter, most of the time things have happened. Once planes start falling, you started doing stuff. So the number of planes that fell decreased. Well, if children start dying on car accidents, so let's do something so children don't die in car accidents. So of course, if by definition you're still answering some questions about a long data time series, well, the chances are you're already probably taken some of the steps to decrease the chance of a raw event occurring here. The phrasing matters. So if you're asking, let's say we will put in being power 2 years from now, well, it depends on are you asking, is he going to be deposed? Is he going to die by natural causes, etc.? And perhaps Tetlok subestimates how payoffs are everywhere. In his book, he presents, okay, so there is a woman in Kansas City, so she has a lot of decisions every day, and so she does probability accessing. Well, he describes her commute and her deciding to leave early so she doesn't get stuck in traffic. As Nassim pointed out many times before, arrival times are fat-tailed in the wrong way. You're never too early, but you can be really, really late. And the consequences of being really, really late are never good. So you're doing a payoff assessment right there when you decide, okay, my commute needs to start here. You're doing a probability assessment. You are doing, well, okay, it depends on where I'm going. I'm going to a party, I can be 15 minutes late. I'm going to catch a train, I might not want to be 30 minutes late. So these kind of decisions are not probabilistic decisions. They are always looking at the consequences. So the next slide.
Let me formalize at one point. When you say they're not probabilistic, in the sense that probability plays much smaller role in your operator than the payoff. Yes. You see, it means an error on probability isn't a big deal. An error on a payoff is a big deal.
Yeah.
Okay. Another comment I'd love to make is that we have this illusion. What is the probability or the expected payoff that I've shown earlier? Let's say the probability function is phi of x, all right, f of x dx. Okay, phi of x cannot be isolated on the fat tails. You see. So but the errors on pi of x or p of x are going to be very small compared to errors on f of x. And you can see that mathematically on the fat tails.
Yes.
So we're not saying that these
don't.
don't count, but the variation around this doesn't matter much.
Yes.
This is the heavy part.
And that's
Or let's say
exactly
that
that's exactly the issue with the definition of the Bria score, is that it's defined on the wrong domain. Because it's
It's
defined.
defined, yeah. Some
domain.
domain matches. This matches perfectly
Yeah,
if you're talking about the binary
yeah.
payoff. You see? If your payoff is binary, then this is a step function, f of x. Okay, f of x is gives you 0 or 1. Then this matches perfectly to the CDF.
Yeah, so let's thinking about Nassim's example before. If I have something that if the payoff on the 0.5% was 1 billion or 1 trillion, a digital stroke at 1 million will pay me the same. Vanilla with the strike 1 million will not pay me the same. So the error on my probability estimation has a much higher consequence.
Mm.
So if you can go, yes,
I wonder if you could
can,
replace
just
the,
because I'm worried about
Sure,
the
sure.
time, Ron. Yes, so yes, algorithm economics. So when you're real world, sequential decisions need to take into account paths that go to ruin. So decisions are dependent on the path and context. For example, of context, I mean the marshmallow experiment. There was recently, okay, people were reproducing the research and said, oh, yes, the decision was wrong because there is the confounder of wealth, that children who are living in the, let's say, poverty, their expectation that a reward tomorrow will happen is much lower because they are used to uncertainty of resources tomorrow, and therefore they discount the two marshmallows later differently than a children who've never had this uncertainty in the, oh, okay, this is going to happen, you're going to get this. And if the children always get this, the children can be certain of the two marshmallows tomorrow, but but they're not. So
yeah, the marshmallow one has several other problems. But let's say that if you start doing a error modeling on top, okay, there's a probability that someone giving you the marshmallow tomorrow will die.
yeah.
Okay,
Yes,
or there's
so,
a guy lying, take it now because he may die. So this is why
so
anything that conflicts with popular wisdom typically is wrong. And sure enough, this turned out to be wrong.
yes.
You
So
have a huge
the
edge
point
in
is,
taking it now.
yeah. So the key thing I think is to make it simple is that even if I can predict the future on average, not necessarily I cannot act according to that average prediction, because if I have, well, let's say that I have, let's say that just go back to the Kelly principle. How much can I bet? Well, depends on my wealth, and the leverage I choose depends on my wealth, on what my current health is. So if you can go to the next slide, which is from O. Peter's paper. So, okay, so if I have many universes, okay, I can look at the average and okay, if I have infinitely many universes, I can look at the average of an ensemble and say, okay, I'm doing this bet this way because I can earn that. Or if I'm rich, I can do many different bets because on average I'll make money. But if I'm poor, I cannot do that because the most likely path is the one that leads to ruin. So knowing the most probable outcome doesn't mean that you are going to be able to follow the most probable outcome. And so therefore, people tend to choose or do the thing that will enable them to survive. So the next slide, there's a comment also when we go to things like, if you look at the typical examples of reinforcement learning, so there's this landscape of positive rewards and negative rewards, and you want to learn the best path to the goal. If the consequences are small and I can do and retry again and train myself into this and get a cumulative experience, then I can overfit and say, okay, I learned this and I learned this thing and I can do good predictions about this problem and such. But not necessarily I'm going to learn, I'm learning about what the processes involved in that. So for those who have looked at the Mysterious Benedict Society, the series, I would suggest you try the book. And in the book, 3 different children have to navigate a maze and go upstairs to a house. So one child learns the trick or the information that enables you to navigate the labyrinth. The other one has a fantastic memory, tried and then memorized the path. And the other one just found a way to bypass the labyrinth. But so in real life, you always try to, if you can learn the pattern, you learn the pattern because then you generalize, or if you can bypass the pattern, if there is a big risk, as Nathan says, so there's this big left tail, okay, then truncate it, then not be exposed to it. But it's not, and one should not try to just overfit and try to learn this small problem. So the next slide, I'll go back to Tetlock's paper, which is why forecasting has been successful in that term. So the point of the division of labor stuff is sometimes kind of a matter of washing of responsibilities. So I want to use something, I want to look at some research and some probability estimates in order to justify a decision that I already have. So you can see that although the whole world could look at the research in COVID, you have different presidents making different decisions. But everyone has internet, everyone has access to every research. So why is that? So why is there different outcomes? Well, because you have such a multiple, because everyone can produce research and everyone can use these numbers as they want.
Sorry, Marcos, you have many slides because at some point I have to hop. I have an appointment.
Yes. Okay, so let's see. And
James had to leave.
So yes. Okay, so, and also there is the point of, Fergal said, well, people will forgive you if you're wrong at the same time as the other ones. So if something happens and everyone is wrong, no one can be predicted. It was your favorite excuse. There was a 10 sigma event or something like that, or whatever. And so you also have this problem of the division of labor stuff in which I can do stuff like, because there is no personal liability for my decisions, I can kind of do stuff without worrying about the outcome for myself. And also, if you look at the next slide, most systems that matter are complex. So feedback can we go to, yes, so feedback cuts it both ways. So so if the system has this momentum where confidence, where good numbers get confidence in the economics and such, you have this momentum and therefore enables you to just predict things as they are and you are correct most of the time. But the problem is that because the perceptions around your communications of the model change the system, that feedback might make the system more fragile. So that phrase is commonly attributed to Galbraith, but according to the Oxford Quotations book, it's from another economist, Ezra Solomon. And that's so some of the tools, well, I personally like the idea of starting with a more general prior, let's say start with the student D with a low degree of freedom, and see if there is anything that changes you from that, or that makes your degree goes from 3 to 2 or something like that. You have to be aware of managed processes. Let's say that you're forecasting a packet currency. Well, you can forecast it's going to be pegged until the end of the world, but once the surprise hits, well, you lose everything. The point is that you need to be aware that that not every data point is equally informative. So an interesting example is that, let's say that you have a regime switching model. Every new point only tells you things about the probability of switching, but not the dynamics of the other regime, because you have not observed the other regime yet. And the only way with getting data from slope of tail is not with binaries, is from something that has a payoff that increases. So as we discussed with the options, few options are enable you to get a much richer distribution idea of the possible distribution than the binary payoffs. So I guess that there is there are other things that I would like to discuss, like, for example, how the, let's say, forecasting volatility is complicated because volatility is changing a lot and such. But this is a discussion on raw volatility modeling. It's another presentation on itself. But this is what I try to get to complement what James and Fergal discussed before.
Okay, so I think
Yes.
I think robust discussion, and it's already late. We've been here for 2.5 hours, so I think I'm not going to show my slides. Let's let everyone go, and maybe we have a follow-up session on some new topics. If anyone in the audience would like some topics, just put us on Twitter. And yeah, it'd be very nice to carry on engaging. So thank you very much to our speakers. Thank you, Nassim, for presenting, James and Fergal and Marcos for their presentations, and till we meet again pretty soon, hopefully.
Thanks a lot. Can you put the recording off for 1 sec?
I think the recording's actually been off for a while.